Hi, my name is Anthony Bober, and I'm going to be finding the relationship between mass diffusive flux and molar diffusive flux in this problem. So what we have here is a capillary, and now it's closed around the outside, and we have a wall in between two ideal gases, A and B. Now what we're going to do is we're going to let both of these gases, we're going to remove the wall, let both gases mix completely. And what we want to do is find the relationship between molar there we go. Between molar diffusive flux of a component, I'm going to use component A as an example, and mass diffusive flux of component A. Now, before we get into this, one thing we should keep in mind is that when we remove this wall and the gases begin to mix, for every mole of A that moves to the right in the positive direction, a mole of B is going to move to the left in the negative direction. And it's a one-for-one exchange, a mole for a mole. So what ends up happening is that there is no net movement of moles of total gas. There is a positive molar flux of A in the positive direction to the right, and a negative molar flux to the left. But when you combine them and you look at the overall motion of the moles, there is no net movement, which means that the molar flux of A equals the molar flux of B. 1 mole is exchanged for 1 mole, but they're in opposite directions. So we will add in our negative sign. And then when we look at the molecular or the molar flux of everything, that equals the summation of the components, the molar flux of A plus the molar flux of B. Again, since these two are equals and opposites, that means that this equals 0. So the overall molar flux is 0. Okay, now to find the relationship between these two, I think a good place to start is going to be to look at the relationship between the molar flux and the mass flux. And if we were going to write out that relationship, it would be the mass flux of component A equals the molar flux of component A multiplied by the molecular weight of component A. And this is just a simple unit conversion that relates the two. Now, what we might want to say is that, okay, this relationship would also hold true for the relationship between the diffusive fluxes. And we would want to write the mass diffusive flux equals the molar diffusive flux multiplied by the molecular weight. And this is a good guess, but this is actually not true. We're going to go a different way to find the relationship, and we will see how this is different from what the relationship really is. So what I'm going to do is write down the definitions. So the molar diffusive flux of component A is equal to the concentration of component A multiplied by the velocity of component A. We're going to subtract the average molar velocity of everything. And then for the mass diffusive flux of component A, that will be equal to the mass concentration of component A multiplied by the velocity of component A, and we will subtract the average mass velocity of everything. So since we want to relate these two variables, we can see here that this velocity of A term appears in both of them. So this is actually what we're going to use to relate the two. Now, something we should consider is that the average molar velocity and how it relates to the molar flux, the total molar flux. Since we have 1 mole of A moving to the left, or moving to the right, and we have 1 mole of B moving to the left, that means that the moles of A have a positive molar velocity, and the moles of B have a negative molar velocity. And since since we're taking the average molar velocity, that would actually cause the average molar velocity to be 0, since we have positives and negatives from the movement of the moles. Another way to look at this is to write down the definition of total molar flux, which equals the concentration times the average molar velocity. Since we already know that the molar flux is equal to 0, we know that the concentration is non-zero, which means that the average molar velocity must be 0. And that's actually really convenient for us because we can just cross this term out. Now we're left with the molar diffusive flux of component A equals the concentration of A multiplied by the velocity of A. And I'm going to rewrite this to solve for the velocity of component A. So when we rearrange it this way, now we have this, and what we're going to do is we're just going to substitute that right in here to this equation for mass diffusive flux. So the mass diffusive flux equals the mass concentration multiplied by the molar diffusive flux divided by the molar concentration minus the average mass velocity. So this right here is actually the relationship between the two, between mass diffusive flux and molar diffusive flux. But we're going to take it a little bit further. We're going to simplify a few things and make a few substitutions to make it a bit more understandable. So the first thing we want to look at is this right here. This is mass concentration over molar concentration. And we're just going to take a look at the units. We have mass of component A over total volume divided by the moles of component A over the total volume. These volumes cancel. We're left with mass of A over moles of A, which equals the molecular weight of A. Now I'm going to substitute this in and write it over here on the left. So we have the mass diffusive flux of A equals the molar diffusive flux of A multiplied by the molecular weight of A. Now this mass concentration will distribute in to the parentheses, so we have the mass concentration of A multiplied by the mass average velocity. Now the next step we want to do is to look at this mass average velocity. So I'm going to write out the definition for it. Mass average velocity equals the mass concentration of A multiplied by the velocity of A plus the mass concentration of B times the velocity of B, all divided by the total mass concentration. So we're going to make a small substitution into this problem to be able to simplify a little bit. And we're going to take this relationship right here, we're going to plug that in. And we're going to do the same thing for the velocity of B. Now, we solved for the velocity of A here, but if we were to solve for the velocity of B, we would do it in the exact same way, and we would come up with the exact same expression. But it would be the velocity of B equals the molar diffusive flux of B divided by the concentration of B. It would be the same thing, just B instead of A. So I'm going to make that substitution. We have the mass concentration of A times the molar diffusive flux of A over the concentration of A plus the mass concentration of B, that's a plus, multiplied by the molar diffusive flux of B over the concentration of B, all divided by the total mass concentration. Scroll down here. And we have this right here. This is mass concentration over molar concentration. And we already said over here on the right that this is equal to molecular weight. So I'm going to make that substitution. And we get molar diffusive flux times molecular weight plus molar diffusive flux of B times molecular weight of B, all over total mass concentration. Okay. Now, the next thing we should consider is the definition of total molar diffusive flux. This is equal to the summation of its components of A, molar diffusive flux of A plus molar diffusive flux of B. That equals 0 from the definition, excuse me. Now this means that the molar diffusive flux of A equals the molar diffusive flux of B, but it is the opposite. It's a negative sign. And since that's the case, we can rewrite this expression up here as molar diffusive flux of A times the difference in molecular weights of A and B. All over total mass concentration. Okay? And again, that is equal to mass average velocity of everything. So now what we will do is we will just shove that right into here. What we will end up with is mass diffusive flux equals molar diffusive flux of A times the molecular weight of A minus the mass concentration of A times the molar diffusive flux of A times the difference in molecular weights of A and B divided by the total mass concentration. Now, we're going to simplify one more time. We're going to look at the units of these two mass concentrations. Mass concentration of A over total mass concentration. That's going to equal the mass of A over the total volume divided by the total mass over the total volume. Again, these volumes cancel. We're left with mass of A over total mass, and that is the mass fraction of A. Now finally, we're going to rewrite this one last time and get the mass diffusive flux of A equals the molar diffusive flux of A times the molecular weight of A minus the mass fraction of A times the molar diffusive flux of A times the difference in molecular weights of A and B. And this is the relationship between the two. This is what we were looking for. And if we actually go back to the top here, where we were looking at we said initially could be the relationship with just the molecular weight, we said that this is not true. And if we look back down here, we can actually see that term, that appears in this equation. But what that doesn't account for is this second term over here, and that is what the difference is. And that's why our above equation up here was not true. So thank you for watching, and I'll see you in the next video.